Alcohols are organic molecules that contain one or more hydroxyl groups attached to a carbon atom or atoms as shown in the illustration. By contrast, phenols contain one or more hydroxyl groups attached to a carbon in an aromatic ring. In phenols, the carbon attached to the hydroxyl group is sp2 hybridized. Alcohols and phenols can be classified based on how many hydroxyl groups are present. Monohydric alcohols and phenols have one hydroxyl group. Dihydric alcohols and phenols have two hydroxyl groups, while trihydric alcohols and phenols have three hydroxyl groups. Monohydric alcohols can be classified on the basis of the nature of the carbon atom attached to the hydroxyl group. These carbons are either sp3 or sp2 hybridized. We will first consider hydroxyl groups attached to sp3 hybridized carbons. In a primary alcohol, the carbon attached to the hydroxyl group is linked to one other carbon-containing group or to none of the carbon-containing group, as shown in the illustration. In a secondary alcohol, the carbon to which the hydroxyl group is linked is attached to two carbon-containing groups. In a tertiary alcohol, the carbon linked to the hydroxyl group is bonded to three carbon-containing groups. An allylic carbon is a carbon atom bonded to a carbon-carbon double bond. Note that the allylic carbon is sp3 hybridized. An allylic alcohol has a hydroxyl group attached to an allylic carbon. Allylic alcohols can also be characterized as primary, secondary, or tertiary. As we saw before, a primary alcohol has one other carbon group attached to the allylic carbon. Secondary allylic alcohols have two carbon-containing groups joined to the allylic carbon. Tertiary allylic alcohols have three carbon groups bonded to the allylic carbon. A benzylic carbon has an sp3 hybridized carbon bonded to an aromatic ring. Thus, we can describe a benzylic alcohol as having a hydroxyl group attached to a benzylic carbon. The molecules illustrated here are examples of benzylic alcohols. Benzylic alcohols can also be classified as primary, secondary, or tertiary, depending on the number of carbon groups bonded to the benzylic carbon as shown. Here is a problem for you to try. Classify these alcohols as primary, secondary, or tertiary alcohols. Molecules A and B are both secondary alcohols. In both A and B, the carbon bonded to the hydroxyl group is attached to two other carbons. Molecules C and E are tertiary alcohols. The hydroxyl bonded carbon is bonded to three other carbons. Molecule D is a primary alcohol. Only one carbon-containing group is attached to the hydroxyl bonded carbon. A vinyl carbon is a carbon atom double bonded to at least one other carbon atom. Vinyl carbons, which are also called alkenyl carbons, are sp2 hybridized. A vinylic alcohol contains a hydroxyl group attached to a vinyl carbon. Note that the vinyl carbon is sp2 hybridized. Can you classify these structures as allylic or vinylic alcohols? Structure A shows a vinylic alcohol. Notice how the hydroxyl group is linked to a carbon participating in a carbon-carbon double bond. Structure B shows an allylic alcohol. The hydroxyl group is bonded to a carbon that is adjacent to a carbon-carbon double bond. Now that we understand the classification of alcohols, let's turn to their nomenclature. The common names of alcohols are derived from the name of the alkyl group with a Y, L ending, plus the word alcohol. For example, the alcohol with the formula CH3OH, shown on the left, is commonly called methyl alcohol. It contains only one carbon, which corresponds to a methyl group. The molecule on the right has a 4-carbon chain in a straight line. This corresponds to N-butyl alcohol, where the N indicates an unbranched carbon chain. In IUPAC nomenclature, the alcohol name is derived from the alkane name of the longest continuous carbon chain. Drop the E from the alkane name and replace with the suffix OL to determine the alcohol name. The location of the hydroxyl group and additional substituents are indicated by using the numbers of the carbon atoms to which these are attached. Let's look at the same molecules we used a little while ago to learn about common names. In the IUPAC system, methyl alcohol with the formula CH3OH is called methanol. N-butyl alcohol is called butan-1-ol. Give the IUPAC names of these structures. Try to find the names on your own before checking the answers. When naming organic compounds, remember to find the longest continuous carbon chain. Start counting the carbons at the end of the chain nearest to the hydroxyl group. In molecule A, the longest continuous chain has 5 carbons. Start counting from the right-hand side of the molecule at the end nearest to the hydroxyl group. Notice that the hydroxyl group is on carbon 2. There is a methyl group at carbon 3. So, the correct name of this molecule is 3-methyl-2-pentanol. In molecule B, the longest continuous chain has 8 carbons. If we start counting carbons at the left end of the chain, closest to the hydroxyl group, we see that the hydroxyl group is on carbon 3 and there is an ethyl group on carbon 4. So the correct name of the molecule B is 4-ethyl-3-octanol. Some alcohols have multiple hydroxyl groups. To name diols and triols, start with the alkane name of the longest continuous carbon chain that contains the hydroxyl groups. The E of the alkane name is retained, and the ending OL is added. The appropriate multiplicative prefixes di, tri, etc. are used to indicate the number of hydroxyl groups present. Numbers in the name then give the locations of the hydroxyl groups. For the example shown here, the longest continuous chain has 5 carbons. We have to start numbering carbons at the right, closest to the hydroxyl groups. Notice that the hydroxyl groups are attached to carbons 2 and 3. So, this molecule is named 2,3-pentane-diol. Alternatively, you may see it written as pentane 2,3-diol. Can you write the IUPAC names of these alcohols? Try to do this on your own before proceeding. Remember to work backwards from the longest continuous carbon chain that contains more than one hydroxyl group. Molecule A has a 4-carbon chain and 2 hydroxyl groups attached to carbon 2. Hence, its IUPAC name is butane 2,2-diol. Molecule B has a 3-carbon chain with 1 hydroxyl group on each carbon. Its IUPAC name is 1,2,3-propane-triol, and the common name is glycerol. Molecule C has a carbon backbone containing 6 carbon atoms. Counting from the right, there are hydroxyl groups at carbons 2 and 4, and a methyl group at carbon 5. It is 5-methyl-2,4-hexane-diol. Cyclic alcohols are named in a similar manner. Count the number of carbon atoms in the ring. Use the prefix cyclo and the alkane name for the number of carbons in the ring. Drop the E from the alkane name and replace it with the suffix OL. The location of the hydroxyl group on the ring is considered to be carbon 1. Look at the molecule illustrated here. The ring has 5 carbon atoms, so this is cyclopentanol. Practice is essential to mastering organic nomenclature. Can you name these alcohols? Remember that the location of the hydroxyl group is considered to be carbon 1, so start counting there. If there is a choice of numbers, count to get the lower numbers for substituents. So, molecule A contains a 6-member carbon ring with a hydroxyl group and a methyl group. Molecule A is a 2-methyl cyclohexanol, not 6-methyl cyclohexanol. Molecule B contains a 3-member ring with a hydroxyl group and a chlorine substituent. Its correct name is 2-chlorocyclopropanol. Molecule C has a 4-member ring with a hydroxyl group and a bromine atom both attached to the same carbon. Molecule C is a 1-bromocyclobutanol. Let's turn our attention to the class of organic molecules called phenols. Phen is an old name for benzene. So the benzene containing 1 hydroxyl group is known as phenol. Although the systematic name is benzanol, phenol is an accepted IUPAC name. We can use this as the basis for naming phenol derivatives. Toluene is an important benzene derivative. It has 1 methyl group attached to the aromatic ring. Cresol is the name for toluene molecules that have 1 hydroxyl group in addition to the methyl group. There are actually 3 isomers for cresol. The isomers for cresol can be named as phenol derivatives 2-methylphenol, 3-methylphenol, and 4-methylphenol. We can also introduce the use of the prefixes ortho, meta, and para to name benzene derivatives. Ortho refers to 1,2-disubstituted benzenes. Similarly, 2-methylphenol, shown on the left, can also be named as orthocresol. Meta is used to refer to 1,3-disubstituted benzenes. So, 3-methylphenol, shown in the center, is also called metacresol. Finally, the prefix para is used for 1,4-disubstituted benzenes. Therefore, 1,4-methylphenol shown on the right is also called paracresol. In IUPAC nomenclature, dihydroxybenzene derivatives are named as diols. Numbers give the locations of the hydroxyl groups. Shown here are 3 examples from left to right. They are benzene 1,2-diol, benzene 1,3-diol, and benzene 1,4-diol. However, the dihydroxybenzene derivatives are actually better known by their common names. Benzene 1,2-diol is known as catechol or pyrocatechol. Benzene 1,3-diol is commonly referred to as resorcinol. Hydroquinone, or just quinol, is the common name for benzene 1,4-diol. Let's do some more practice problems. Give the IUPAC names of the compounds shown here. Remember, the location of the hydroxyl group is carbon number 1. So, molecule A can be named 2,6-dimethylphenol. Its common name is 2,6-xylenol. Molecule B is 4-chlorophenol or parachlorophenol. Molecule C is 1,2,3-benzene triol. It is commonly known as pyrogallo. Ethers are a class of organic molecules that contain a bridging oxygen between 2 carbon-containing groups. The carbon groups may be either aliphatic or aromatic. Ethers can also be thought of as a substituted alkane with an alkoxy or aryloxy group. Ethers can be classified in several ways. Simple or symmetrical ethers have 2 identical carbon groups on either side of the oxygen. Mixed or unsymmetrical ethers have different carbon groups on either side of the oxygen. The common names of ethers give the names of the alkyl or aryl groups in alphabetical order, followed by the word ether. For example, the common name of the ether shown here is ethyl-methyl ether. If the ether is symmetrical, use the prefix di plus the name of the alkyl group name, add the word ether at the end. The ether shown here has the common name diethyl ether. IUPAC rules for ether nomenclature are based on descriptions of ethers as alkoxy-substituted alkanes. The larger group is considered to be the parent hydrocarbon. A number gives the location of the alkoxy substituent. This makes the IUPAC system more versatile than the common names for ethers. Consider the molecule shown here. It has a methyl group and an ethyl group. The ethyl group contains more carbons. Therefore, the ethyl group is considered to be the parent chain with a methoxy substituent. In the IUPAC system, this ether is named methoxyethane. Here are some problems for you to try. Give the IUPAC names of the compounds shown here. They are all ethers. Remember that the longer chain is considered to be the parent chain. Molecule A is ethoxybenzene. Its common name would be ethyl phenyl ether. Molecule B has a 5-carbon chain with an ether linkage attached to a methyl group at carbon 3. Thus, molecule B is named 3-methoxypentane. Molecule C contains a methyl group and a propyl group. Since the longer chain has 3 carbons, molecule C is named methoxypropane. Its common name would be methyl propyl ether. Molecule D has a 6-carbon substituted alicyclic chain with an ether linkage attached to the ethyl group at carbon 2 as shown. Therefore, its IUPAC name is 2-ethoxy-1,1-dimethyl cyclohexane. Molecule E has a 3-carbon chain with an ether linkage attached to an ethyl group at carbon 2. Its IUPAC name is 2-ethoxypropane. We have figured out the names for many molecules in this module. Now, let's practice going in the other direction. Draw the correct structures for these molecules. Try to work these out on your own before checking the answers. When drawing molecules from names, the parent chain is given last in the name. Remember to work backwards. Molecule 1 is 2,3-diethyl phenol. Start by drawing a phenol ring. The location of the hydroxyl group is position 1 on the ring. Then, add ethyl groups at carbons 2 and 3. Molecule 2 is 2-ethoxybutane. Start with a butane chain which has 4 carbon atoms. At carbon 2, insert an ether linkage to an ethyl group. Molecule 3 is 2-methyl-2-butanol. Start with a 4-carbon chain from butane. Place a hydroxyl group on carbon 2 and then put a methyl group on the same carbon. Molecule 4 is 2-propan-1-ol. Start with a 3-carbon chain since it is a propane derivative. Put a hydroxyl group on carbon 1. The double bond starts with carbon 2. The hydroxyl group outranks the double bond in IUPAC nomenclature. The last molecule is 1,3-cyclohexane diol. Start with a 6-member ring. Put a hydroxyl group on 1 carbon. That position is carbon number 1. Put a second hydroxyl group on a carbon atom 2 positions away. Let's start by looking at the hydroxyl group in alcohols. The oxygen is sp3 hybridized. It forms a sigma bond with end-to-end overlap with an sp3 hybrid orbital of carbon. In methanol, the carbon-oxygen-hydrogen bond angle is 108.9 degree, slightly less than the tetrahedral bond angle of 109.5 degree due to the repulsion between the lone pairs on the oxygen atom. The carbon-oxygen bond length is 142 picometers, and the oxygen-hydrogen bond length is 96 picometers. Phenol, which is a planar molecule, also has a hydroxyl group, but the oxygen forms a sigma bond with an sp2 hybridized carbon. The carbon-oxygen-hydrogen bond angle is 109 degrees. Notice that the carbon-oxygen bond length in phenol, which is 136 picometers, is slightly shorter than in methanol. The carbon-oxygen bond length is shorter in phenol because the bond has partial double bond character. The lone pairs on oxygen have conjugation with the aromatic ring. Methoxymethane is a typical ether with a bridging oxygen group. The 4 electron pairs around the oxygen, 2 bond pairs and 2 lone pairs have an approximately tetrahedral arrangement. The bond angle of 111.7 degrees is slightly greater than tetrahedral due to the repulsion between the two bulky alkyl groups. Notice that the carbon-oxygen bond length is almost the same as in alcohols. Let's focus our attention on synthetic routes to prepare alcohols. The first method we'll discuss is the preparation of alcohols from alkenes by acid-catalyzed hydration. Here's the general reaction. An alkene reacts with water in acidic conditions to form an alcohol. This method is used less frequently for lab-scale synthesis of alcohols. If the alkene is unsymmetrical, meaning that different groups are attached to the carbons of the double bond, then two possible alcohol products could form. How do we determine which alcohol will be the major product of the reaction? Markovnikov's rule allows us to predict the regioselectivity. The hydrogen will add to the carbon with more hydrogen atoms bonded to it. The hydroxyl group adds to the carbon with fewer hydrogen atoms bonded to it. Let's work through a problem to show the application of Markovnikov's rule in acid-catalyzed hydration of alkenes. Propene reacts with water in a dilute solution of sulfuric acid. What are the two possible products of the reaction? Identify the major product. Start by drawing the structure of propene. Notice that one carbon in the double bond has one hydrogen atom attached, while the other has two. Draw the two possible alcohols that could form. Using Markovnikov's rule, we can determine that the upper product shown is the major product of the reaction, the H atom added to the carbon with more hydrogen atoms. The lower structure is the minor product of the reaction. It's important that you understand the mechanism of acid-catalyzed hydration of alkenes. We'll go through each step in detail. Step 1 involves the formation of a carbocation. The carbon-carbon double bond becomes protonated to form a stable carbocation. Then, water, acting as a nucleophile, attacks the carbocation to form an oxonium ion. Finally, the oxonium ion loses a proton to water, acting as a loose base to form the alcohol. A second synthetic route to prepare alcohols is by the hydroboration oxidation of alkenes. This can be summarized as a two-step process. First, the alkene reacts with diborane to form a trialkyl borane compound. The series of steps that forms the addition product trialkyl borane is shown here. Then, the trialkyl borane is oxidized by hydrogen peroxide in aqueous sodium hydroxide to form the corresponding alcohol. Note that water is not a reactant in the hydroboration oxidation of alkenes. A particularly useful feature of this synthetic route is the resulting anti-Markovnikov's hydration of the alkene. In contrast to acid-catalyzed hydration, hydroboration oxidation results in the hydroxyl group attaching to the carbon with more hydrogen substituents. Let's do a practice problem. Draw the structure of the main organic product formed when 2-methyl-2-butane is reacted with diborane in a suitable solvent, followed by treatment with basic hydrogen peroxide. Start by drawing the structure of the reactant. Since this reaction uses hydroboration oxidation of the alkene, the major product will show anti-Markovnikov's addition. Therefore, the hydroxyl group will attach to the carbon with more hydrogens, as shown here. Another route for the preparation of alcohols is by the reduction of aldehydes and ketones. This involves the addition of hydrogen gas in the presence of a suitable metal catalyst, such as platinum, palladium, or nickel. The overall reaction for the catalytic reduction of an aldehyde to a primary alcohol is shown here. This method also works for the reduction of ketones. Aldehydes and ketones can also be reduced by treating them with reducing agents such as sodium borohydride or lithium aluminium hydride. The overall reduction of a ketone to form a secondary alcohol is shown here. Aldehydes can also be reduced in a similar fashion. Can you answer this question on your own? Give the structure and IUPAC name of the product expected from the catalytic reduction of 2-pentanone. When you draw the correct structure of 2-pentanone, you should immediately recognize it as a ketone, as the carbonyl group is in the middle of the chain. The catalytic reduction of a ketone produces a secondary alcohol. The product is 2-pentanol. Alternatively, you could have used sodium borohydride or lithium aluminium hydride instead of hydrogen gas with a metal catalyst. The fourth route for alcohol preparation involves the reduction of carboxylic acids using lithium aluminium hydride. Carboxylic acids are very difficult to reduce, so this process requires a very strong reducing agent, lithium aluminium hydride. The overall reaction given here shows that carboxylic acids can be reduced to primary alcohols. This is actually a two-step process. First, treatment with lithium aluminium hydride, followed by the reaction with water. Lithium aluminium hydride is actually very expensive, so the use of this reaction is somewhat limited. Since carboxylic acids are so difficult to reduce directly, a fifth synthetic route is used in industrial settings. The carboxylic acid is converted into an ester, which is then reduced. The first step of this process converts the carboxylic acid into an ester. The carboxylic acid is reacted with an alcohol to form an ester molecule and water. Esters are much easier to reduce than carboxylic acids. The ester can be catalytically hydrogenated to form two alcohols. This process requires a specialized catalyst, which is why this process is typically carried out in industrial settings. It's time to try another practice problem. You wish to make a cyclopentyl methanol, shown here, by using lithium aluminium hydride in diethyl ether. Determine the structure of an appropriate starting material. You need to work backwards from the desired product. Remember that using lithium aluminium hydride involves two steps that should be listed over the arrow. An appropriate starting material would be cyclopentane carboxylic acid. Since the desired product is a primary alcohol, you could also start with the appropriate aldehyde instead of the carboxylic acid. Grignard reagents are important in many chemical syntheses. Grignard reagents are alkyl magnesium halides. General formula for a Grignard reagent is RMgX, where R is an alkyl or aryl group. Shown here is methyl magnesium bromide, an example of a Grignard reagent. Grignard reagents provide a sixth route for preparing alcohols. Grignard reagents can be reacted with aldehydes and ketones to make alcohols in a two-step process. The first step involves nucleophilic addition of the Grignard reagent to the carbonyl group to form an alkoxy magnesium halide adduct. Then the adduct is hydrolyzed to form an alcohol. Grignard reagents are useful in preparing a variety of different alcohols. When Grignard reagents are reacted with methanol, commonly known as formaldehyde, the reaction makes a primary alcohol with one more carbon than present in the R group of the Grignard reagent. When a Grignard reagent reacts with an aldehyde other than methanol, the reaction produces a secondary alcohol. The reaction of a Grignard reagent with a ketone produces a tertiary alcohol. Try to answer this question on your own before checking the answer. Give the structure and IUPAC name of the product expected from the reaction of pentanal with ethyl magnesium bromide. Start by drawing the structures of the two reactants. Recall that an aldehyde reacting with a Grignard reagent forms a secondary alcohol. This reaction will form 3-heptanol as shown here. Let's turn our attention to the preparation of phenol. Phenol, also known as carbolic acid, was first isolated from coal tar in the 19th century. Phenol can be synthetically prepared from benzene derivatives. The first route for the preparation of phenol is from haloarenes. In the first step of this process, a haloarene is reacted with sodium hydroxide at high temperature and pressure. In the equation shown here, chlorobenzene is reacted with sodium hydroxide to form sodium phenoxide. Then, the sodium phenoxide is acidified to form phenol. A second synthetic route involves benzene sulfonic acid. This was the first method developed for the preparation of phenol. In the first step of this process, benzene reacts with hot concentrated sulfuric acid, which is sometimes called oleum. In the second part of the process, the benzene sulfonic acid that results is treated with molten sodium hydroxide and subsequently acidified to form phenol. A third synthetic route uses diazonium salts. In the first step of this process, an aromatic primary amine is reacted with nitrous acid from NaNO2 and HCl to form a diazonium salt. Then, the diazonium salt is hydrolyzed with warm water or dilute acid to phenol. The overall equation is shown here. A fourth route to phenol uses cumene or isopropyl benzene. This is the most common industrial synthetic method for phenol. In the first step of this process, cumene is oxidized in air to form cumene hydroperoxide. This is then treated with dilute acid to form a phenol. Acetone is the other product of this reaction. Alcohols and phenols consist of two main parts: an alkyl or aryl group and a hydroxyl group. The hydroxyl group chiefly determines the physical properties of the alcohols and phenols. The nature of the alkyl or aryl group does modify these properties to some extent. The boiling points of both alcohols and phenols increase as the length of the carbon chain increases. as shown in the table here for some primary alcohols. This is due to increasingly strong London forces as the length of the carbon chains increase. What is the effect of branching on the boiling point of alcohols? Use the information in the table. The table shows 3 butanol isomers, which all have the same molecular formula. As the branching of the carbon chain increases, the molecules attain a spherical shape and the surface area decreases. As a result, the van der Waals forces of attraction become weaker, and therefore the boiling point decreases with an increase in branching. Therefore, among the isomers of butanol, tertiary butyl alcohol 2-methyl-propan-2-ol has the lowest boiling point, as shown in the table. Alcohols and phenols have boiling points higher than other classes of organic molecules, such as hydrocarbons, ethers, haloalkanes, and haloarenes, with similar molecular masses. For example, the boiling point of ethanol is considerably higher than that of methoxymethane or propane, although all the 3 substances have very similar molecular masses. Both alcohols and phenols can participate in intermolecular hydrogen bonds due to the presence of the polar hydroxyl group. Thus, alcohols and phenols have higher boiling points than ethers or hydrocarbons, which cannot participate in hydrogen bonding. Alcohols and phenol can both form hydrogen bonds with water, and so both are water-soluble. The solubility of substituted phenols is very low in comparison to phenol. It should be noted, however, that as the alkyl or aryl groups get larger, the solubility decreases. Ethanol and other low molecular mass alcohols are completely miscible in water. They can dissolve in water in any proportion. Let's apply our knowledge to answer some questions. Which of these molecules would you expect to have the higher boiling point? It's helpful to draw structures for these types of problems. Essentially, you need to determine which molecule in each pair has the stronger intermolecular attraction. For set A, 1-heptanol has the higher boiling point because it has the longer carbon chain. For set B, 1-propanol has the higher boiling point. 1-propanol with its hydroxyl group can participate in intermolecular hydrogen bonds, while the ether methoxymethane cannot. For set C, 1-hexanol has the higher boiling point. Its carbon chain is unbranched, giving it stronger London forces than the branched chain in its structural isomer 2,3-dimethyl-butane-1-ol. We'll start with the term nucleophile. The word nucleophile means nucleus seeking. In other words, a nucleophile typically has a lone pair of electrons or negative charge that it can use to make a covalent bond. A nucleophile can be described as a Lewis base or an electron pair donor. The chloride ion shown here is an example of a nucleophile. Another important term is electrophile. The term means electron seeking. An electrophile typically has a positive charge and an empty orbital. Electrophiles are Lewis acids or electron pair acceptors. The cations shown here are both examples of electrophiles. Alcohols are a versatile class of compounds. They can act as nucleophiles or as Lewis bases. Note the lone pairs on oxygen in the alcohol formula. When alcohols act as nucleophiles, the bond between the oxygen and the hydrogen is broken. Protonated alcohols act as electrophiles. Electrophiles will react with electron-rich species such as nucleophiles. In the reaction shown here, the nucleophile chloride ion attacks carbon. The bond between the C and the O breaks in the alcohol as the products form. Essentially, we can separate the reactions of alcohols in two major classes. Reactions involving cleavage of the oxygen-hydrogen bond, which occur for both alcohols and phenols, and reactions involving cleavage of the carbon-oxygen bond. Only alcohols undergo reactions that break the carbon-oxygen bond. We'll start with the reactions that involve the cleavage of the oxygen-hydrogen bond in alcohols and phenols. Alcohols and phenols react with active metals, such as sodium, potassium, and aluminium to form alkoxides or phenoxides and hydrogen. The general formula of the reaction is shown here. Notice that the OH bond breaks as the metal alkoxide forms. Try to solve this problem on your own before checking the answer. Write the chemical equation for the reaction of propan-1-ol with potassium. A reaction between an alcohol and potassium metal will form a potassium alkoxide. In this case, potassium propoxide forms as shown here. Phenols react with aqueous sodium hydroxide to form sodium phenoxides. Water is a byproduct of the reaction. Note that alcohols do not react with aqueous sodium hydroxide because they do not have enough acidity. The reactions we just studied illustrate that alcohols and phenols are acidic compounds. Phenols are comparatively more acidic than alcohols. They are Bronsted acids or proton donors. As the equation here shows, they can donate a proton to a stronger base. Alcohols can donate protons because the oxygen-hydrogen bond is polar. Since oxygen is more electronegative, it has a partial negative charge. The hydrogen has a partial positive charge. Let us now understand why primary alcohols are more acidic than secondary alcohols, which in turn are more acidic than tertiary alcohols. The presence of alkyl groups in alcohols increase the electron density around oxygen by the inductive effect. As alkyl groups donate electron density to the oxygen-hydrogen bond becomes less polar. It then becomes difficult to remove an H+ ion from the alcohol. The inductive effect explains the relative acidities of alcohols. Methyl and primary alcohols, which have the lowest degree of the inductive effect, are slightly more acidic than secondary alcohols. Secondary alcohols are slightly more acidic than tertiary alcohols, which have a strong inductive effect. Alcohols are weaker acids than water. We know this because alkoxide ions react with water to form the alcohol, the conjugate acid, and a hydroxide ion. Since this reaction favors the products, it means that water is a better proton donor than the alcohol. Versatile alcohols can also act as Bronsted bases or proton acceptors. The reaction here shows an alcohol accepting a hydrogen ion or proton from HCl. Phenols are also acidic in nature. Note that the benzene ring acts as an electron withdrawing group. The resonance structures of phenol, shown here, illustrate that the oxygen atom in phenol has a partial positive character. Phenols are Bronsted acids or proton donors. In fact, phenols are stronger acids than water or alcohols. The presence of the aromatic ring leaves less electron density on oxygen. So, the oxygen-hydrogen bond is more polar. This makes the loss of a hydrogen ion more favorable. The phenoxide ion forms when phenol ionizes by losing a hydrogen ion. The resonance structure of the phenoxide ion are shown here. Notice that the negative charge of the ion is delocalized, which stabilizes the ion. On the other hand, in the alkoxide ion, the negative charge is localized on oxygen, which makes it less stable. The charge delocalization favors the ionization of phenol. Note that, in phenol, the charge separation in the resonating structures makes it less stable than the phenoxide ion. Hence, phenols lose a hydrogen ion more readily than alcohols. In other words, phenol is a stronger acid than alcohols. We can also discuss acid strength by comparing acid dissociation constants, or Ka. Strong acids have large acid dissociation constants. pKa values are also used to compare acid strengths. The pKa of any acid dissociation constant is defined as the negative log of the Ka value. Since pKa is a logarithmic function, as the Ka increases, as acid strength increases, the pKa value decreases. Therefore, a higher pKa value corresponds to a weaker acid. Try to reason this problem out on your own. Which one would you expect to have the higher pKa value? Ethanol or phenol? How should their pKa values compare to water? You have learned that phenols are stronger acids than alcohols and water. You also know that water is a stronger acid than ethanol. Finally, you learned that stronger acids have lower pKa values than weaker acids. So, phenol should have a lower pKa than water and ethanol. Water should have a lower pKa than ethanol. You can confirm your reasoning by comparing the actual pKa values. As expected, phenol has the lowest pKa and ethanol the highest. Substitutions on the benzene ring of phenol can alter phenol acidity. The presence of electron withdrawing groups, such as the nitro group, make phenols more acidic. This is especially true when the electron withdrawing groups are in either the ortho or para positions. In these positions, nitro groups allow for resonance structures that stabilizes the phenoxide ion by allowing more delocalization of negative charge. Conversely, the presence of electron-releasing groups, such as alkyl groups on the benzene ring, result in weaker acids for substituted phenols. For example, compare the pKa values of phenol and cresol. Phenol has a lower pKa value than cresol, reflecting that phenol is the stronger acid of the two. Remember that pKa values use a logarithmic scale. It's time to turn our attention back to reactions of alcohols and phenols. One important class of reactions is called esterification. Both alcohols and phenols react with carboxylic acids to form esters and water. This reaction is slow and reversible. Sulfuric acid is used as the catalyst in this reaction. Alcohols and phenols can also react with acid chlorides to form esters. These reactions are carried out in the presence of a base, such as pyridine. The base neutralizes the hydrochloric acid as it forms, which causes the equilibrium to shift right. Additionally, alcohols and phenols can react with carboxylic acid anhydrides to form an ester as well as a carboxylic acid. These reactions are slow and require heating. Try to work out this problem on your own before continuing. Write the structure of the primary product formed when benzoic acid and N-propanol are combined in the presence of sulfuric acid. Start by drawing out the structures of the reactants. You should recognize this as an esterification reaction. Propyl benzoate is the main product of the reaction. One application of esterification is the synthesis of aspirin. Acetylation is the introduction of an acetyl group into alcohols and phenols. When salicylic acid, a carboxylic acid, is mixed with ethanoic anhydride, a carboxylic acid anhydride, acetyl salicylic acid, or aspirin, is the primary product. Acetic acid or ethanoic acid is also formed. Now let's turn our attention to reactions that result in cleavage of the carbon-oxygen bond. Only alcohols show these types of reactions. Alcohols react with hydrogen halides to form alkyl halides and water. The Lucas test for alcohols uses the Lucas reagent, a solution of zinc chloride in concentrated hydrochloric acid. When the insoluble chloroalkane forms, the resulting mixture has a cloudy, turbid appearance. The Lucas test is used to differentiate between primary, secondary, and tertiary alcohols. An alcohol, zinc chloride, and hydrochloric acid are combined at room temperature. A primary alcohol leads to no visible change in the mixture. A secondary alcohol will show cloudiness in about 3 to 5 minutes. A tertiary alcohol turns cloudy almost immediately. Alcohols react with phosphorus tribromides to form alkyl bromides. A general equation is shown here. the phosphorus acid that forms is water-soluble and can be washed away. Another important reaction of alcohols is acid-catalyzed dehydration. You can think of these reactions as the removal of H2O from the alcohol. The alcohol must be treated with a protic acid, which acts as a catalyst for the formation of an alkene. Acid-catalyzed dehydration of primary alcohols requires the use of sulfuric acid. Secondary and tertiary alcohols can be dehydrated under milder conditions using phosphoric acid as a catalyst. In general, primary alcohols are the least reactive, while tertiary alcohols the most reactive towards acid-catalyzed dehydration. Here is a problem for you to try. Draw the structure of the major product formed when 2-methyl-2-propanol is heated with sulfuric acid. You should recognize these conditions as acid-catalyzed dehydration of an alcohol. Start with the structure of the reactant. Remove the OH group and an H from any of the 3 surrounding carbons. They are all equivalent in this molecule. It is very important to understand the mechanism involved in acid-catalyzed dehydration of alcohols. The proposed mechanism takes place in 3 steps. Step 1 involves the formation of a protonated alcohol or an alkyl oxonium ion called tertiary butyl oxonium ion. This step is a fast equilibrium. The second step of the mechanism is the dissociation of the alkyl oxonium ion to form a carbocation, that is tertiary butyl carbocation. This is the slow step or the rate-determining step of the mechanism. The final step of the mechanism eliminates a proton from the carbocation to form an alkene 2-methyl-1-propane. Notice that the hydrogen ion used in the first step of the mechanism is regenerated in this step. This is consistent with acid catalysis. To drive the equilibrium to the right, the alkene is removed as it is produced. Alcohols can also undergo oxidation to form compounds with carbon-oxygen double bonds. These are also sometimes called dehydrogenation reactions, as they involve the loss of hydrogen molecule from the reactant. Notice that the oxygen-hydrogen bond breaks as well as a carbon-hydrogen bond. Depending on the oxidizing agent used, primary alcohols may be converted into aldehydes and ultimately into carboxylic acids. Let's consider the different reaction conditions and their outcomes. When a primary alcohol is treated with acidified potassium permanganate, a very strong oxidizing agent, the alcohol will be converted directly into a carboxylic acid. Chromium 6 oxide or chromic anhydride is another strong oxidizing agent. In anhydrous conditions, it can be used to convert primary alcohols into aldehydes. However, chromic anhydride is highly toxic and environmentally hazardous. An alternative route to the preparation of aldehydes from primary alcohols is to use pyridinium chlorochromate, or PCC. The addition of PCC to a primary alcohol will produce an aldehyde. PCC is also toxic. What reagent would you use to carry out the oxidation of 1-propanol to form 1-propanal? From the structures, we see that this reaction converts a primary alcohol into an aldehyde. Therefore, we don't want to use potassium permanganate, which would make a carboxylic acid. We can use either PCC or chromic anhydride to carry out this reaction. Treating secondary alcohols with chromic anhydride will produce ketones. Try to answer this question independently before checking the answer. Write a balanced equation showing the structure of the primary organic product formed when 2-butanol is treated with chromic anhydride. 2-butanol is a secondary alcohol. Chromic anhydride oxidizes secondary alcohols to form ketones. The product is 2-butanone. Tertiary alcohols don't undergo oxidation reactions. Under strong conditions, that is, using strong oxidizing agents at elevated temperatures, cleavage of carbon-carbon bonds is observed. A mixture of carboxylic acids results. Dehydrogenation reactions of primary or secondary alcohols can also be carried out by passing vapors of the alcohols over heated copper. Under these conditions, primary alcohols form aldehydes, while secondary alcohols form ketones. If vapors of tertiary alcohols are passed over heated copper, dehydration reaction takes place to form alkenes. For example, 2-methyl-2-propanol forms 2-methyl-1-propene when passed over heated copper. As the alkene forms, the OH group and one hydrogen from an alkyl carbon are lost to create a water molecule. Phenols, which can be thought of as substituted benzenes, can undergo electrophilic aromatic substitutions. The hydroxyl group of phenols tends to make the ring more likely to undergo substitution. The hydroxyl group activates the ring to substitution. Phenols undergo these substitution reactions more readily than benzene. The hydroxyl group of phenols tend to direct further substitutions of the aromatic ring to the ortho and para positions, that is, 2 and 4 positions. The hydroxyl group is ortho-para directing because the resonance structures of phenols make the ortho and para positions electron-rich. Notice in the resonance structure shown that the ortho and para positions have extra electron density at those positions. Let's learn about some important substitution reactions of phenols, starting with nitration. If you react phenols with dilute nitric acid at low temperatures, a mixture of ortho and para nitrophenols will be produced. The two isomers of nitrophenol have different physical properties. As the illustration shows, orthonitrophenol can participate in intramolecular hydrogen bonds. The para isomer can participate in hydrogen bonds between molecules. The intermolecular hydrogen bonds hold the para nitrophenol molecules together. The different hydrogen bond arrangements have important effects on the physical properties. Since the ortho isomer has only intramolecular hydrogen bonding, it has weaker intermolecular attractions than the para isomer, with its intermolecular hydrogen bonds. Therefore, orthonitrophenol is more volatile, with a lower boiling point than para-nitrophenol with a higher boiling point. We can use the difference in their boiling points to separate the isomers by steam distillation. Orthonitrophenol is steam volatile, but para-nitrophenol is not. The outcome of nitration of phenol varies with the reaction conditions. When a phenol reacts with concentrated nitric acid, the reaction produces 2,4,6-trinitrophenol, commonly known as picric acid. This reaction occurs in low yield. Picric acid is a stronger acid than phenol because of the presence of 3 electron-withdrawing nitro groups, which facilitate the release of hydrogen ion. It is explosive and was formerly used in artillery and munitions. Picric acid in the laboratory must be stored wet, else explosive metal picrates may form. It is used in several forensic applications: chemical synthesis and gram staining in biology. Another synthetic route with improved yield has also been developed for the synthesis of picric acid from phenol. In the first step of this process, phenol is reacted with concentrated sulfuric acid to form phenol 2,4-disulfonic acid. In the second step, phenol 2,4-disulfonic acid is reacted with concentrated nitric acid to form picric acid. Phenol also undergoes halogenation reactions. The reaction of phenol with bromine gives different products depending on the reaction conditions. Let's look at this in more detail. If phenol is treated with bromine in low polarity solvents, such as chloroform or carbon disulfide, at room temperature, monobromophenols are produced. Unlike benzene, no Lewis acid is needed for this reaction to occur, because phenol is much more reactive than benzene. Both ortho and para isomers form, but the para isomer is the major product due to the steric hindrance at the ortho position. Alternatively, if you treat phenol with bromine water, 2,4,6-dibromophenol is produced as a white precipitate. The equation is shown here. Again, this reaction does not require a catalyst because phenol is quite reactive. Can you solve this problem on your own? Draw the structures of the major products expected when 3-fluorophenol reacts with bromine, in carbon disulfide, and with bromine water. You should recognize that the reaction conditions for part A result in monobromo derivatives. 2 isomers will form, but 4-bromo-3-fluorophenol is expected to be the major product. In part B, the reaction conditions favor multiple substitutions. 2,4,6-tribromo-3-fluorophenol will be the major product. Phenoxide ions are even more reactive than phenol towards electrophilic aromatic substitution. Several important reactions of phenols make use of this enhanced reactivity. In coal-base reaction, sodium phenoxide is prepared and then subsequently heated with carbon dioxide under pressure. carbon dioxide, the neutral electrophile attacks phenoxide ion to form sodium salicylate. The sodium salicylate, when acidified, forms 2-hydroxybenzoic acid or salicylic acid. The ortho position is favored in coal-based synthesis. Here is a problem for you to solve. Draw the structure of the major organic product formed when para-cresol 4-methylphenol is treated with the conditions of Kolb's synthesis. Alkyl derivatives of phenol react in a manner very similar to phenol. Treatment with sodium hydroxide, followed by heating with carbon dioxide at high pressure, and then acidification, forms an ortho-hydroxybenzoic acid derivative. Ramer-Tiemann reaction introduces a CHO group at the ortho position of phenol. The Ramer-Tiemann reaction can be thought of as a two-step process. The first step is treatment with chloroform in the presence of sodium hydroxide to form a substituted benzyl chloride intermediate. Note that, in this reaction, chloroform reacts with sodium hydroxide to form dichlorocarbene, which is a neutral electrophile. The second step is hydrolysis of the substituted benzyl chloride intermediate in basic conditions, followed by acidification, which forms salicylaldehyde. Heating phenol vapors with zinc dust produces benzene as the major organic product. Here, phenol undergoes reduction in the presence of zinc dust to form benzene. Phenols are oxidized more readily than alcohols. Phenols can be oxidized either by chromic acid or silver oxide, a weak oxidizing agent to produce conjugated diketones, which are commonly called benzoquinones. Can you predict the major organic product formed when 3-chloro-1,2-benzene-diol is treated with chromic acid? Since two hydroxyl groups are present, both will be oxidized into ketones. The double bonds need to be rearranged to make the diketone. When exposed to air, phenols will be slowly oxidized into quinones, even in the absence of an additional oxidizing agent. Upon aerial oxidation, phenol forms benzoquinone. Quinones are highly colored compounds. For example, benzoquinone is a bright yellow. Many synthetic dyes are actually quinones. Some quinones have important biological functions. Ubiquinone, or coenzyme Q, is essential for cellular respiration. Vitamin K is needed for proper blood clotting to occur. Two commercially important alcohols are methanol and ethanol. Let's learn about their production, properties, and uses. Methanol has the chemical formula CH3OH. It is commonly referred to as wood spirit or wood alcohol because it was first obtained as a byproduct from the production of charcoal from wood. Methanol is prepared on an industrial scale by the catalytic hydrogenation of carbon monoxide. This reaction requires high temperature and pressure, as well as a zinc oxide chromium 3 oxide catalyst. Methanol is a colorless liquid that is volatile and flammable. Its boiling point is 337 Kelvin. Methanol is highly poisonous. Ingesting as little as 30 ml can be fatal. Smaller amounts of ingested methanol can cause blindness. Methanol is used as a solvent in paints and varnishes. It is used as an antifreeze and windshield wiper fluid. About 50% of all methanol produced commercially is used to make formaldehyde. Ethanol has the chemical formula C2H5OH. It is primarily formed from the fermentation of sugars from various plant materials. First, the enzyme invertase converts the sugar in molasses, sugarcane or fruits into glucose and fructose. Both glucose and fructose have the same molecular formula C6H12O6. Next, the yeast enzyme zymase ferments the simple sugars, glucose and fructose to form ethanol. Carbon dioxide is also released. In winemaking, grapes are the source of sugars and yeast. As the grapes ripen, the sugar content increases. Yeast grows on the outer skin of the grapes. When the grapes are crushed, the sugar and the enzyme zymase come into contact, which initiates the fermentation. Fermentation needs to be carried out under anaerobic conditions. If air gets into the container, the ethanol will be oxidized into ethanoic acid, that is, vinegar, which will ruin the taste of the final product. Zymase activity is inhibited once the alcohol concentration of the wine becomes greater than about 14%. Ethanol is a colorless liquid, which, like methanol, is volatile and flammable. It has a boiling point of 351 Kelvin. Ethanol is used as a solvent for paints, markers, perfumes, and other products. It is used to prepare various organic compounds. It is used as a motor fuel and fuel additive. Many bacterial hand sanitizers contain ethanol. Alcoholic beverages contain ethanol. Ethanol is a central nervous system depressant. In low doses, it leads to fewer inhibitions and reduced concentration. Poor judgment and slow reflexes are also hallmarks of ethanol consumption. In moderate doses, ethanol can cause slurred speech, drowsiness, and damage to the liver and the gastrointestinal tract. In higher doses, ethanol can lead to vomiting, breathing difficulties, and unconsciousness, which can be fatal. Chronic alcohol abuse can cause frontal lobe damage, neurological problems, and dependence. Alcohol and automobiles don't mix. Never drink and drive. To prepare ethanol on an industrial scale, ethene is reacted with steam. This reaction requires high pressure and a phosphoric acid catalyst on a silicon dioxide support. The overall reaction shown here is an oversimplification of the actual process used. Ethanol meant for industrial and commercial uses is made unfit for human consumption by adding certain chemicals. Additives, including copper sulfate, which lends a blue color, or pyridine, which has a foul odor, and even methanol are used to produce denatured alcohol. One way to prepare ethers is by the dehydration of primary alcohols in the presence of an acid catalyst, typically sulfuric acid, at 140 degrees Celsius. Notice that two molecules of a primary alcohol form a dialkyl ether and water. For example, two molecules of ethanol undergo dehydration in the presence of concentrated sulfuric acid at 140 degrees Celsius to form ethoxyethane. This reaction does not work with secondary and tertiary alcohols. Note that secondary and tertiary alcohols produce alkenes via elimination. Ethers can be prepared by the dehydration of primary alcohols by an SN2 mechanism, which means that the reaction involves an attack by a nucleophile and is a bimolecular slow step. In the first step, the ethanol forms an oxonium ion or a protonated alcohol. In the second step, another alcohol molecule attacks the oxonium ion to form a dialkyl oxonium ion. This is the slow step of the mechanism. In the third step, the dialkyl oxonium ion loses a proton to form the ether. Notice that the hydrogen ion consumed in the first step is regenerated in this step. Here is a problem for you to solve. What alcohol would you use to prepare 1-propoxypropane? For problems like this, the best strategy is to work backwards from the product, which is a symmetrical ether. Since there are 3 carbon atoms on either side of the bridging oxygen, we need to use 1-propanol. Here is the overall equation for the synthesis of 1-propoxypropane or dipropyl ether. The reaction conditions drastically affect the outcome of the reaction. Adding sulfuric acid to primary alcohols at lower temperatures favors substitution reactions to form ethers. At high temperatures, however, elimination reactions are favored, which result in the formation of alkenes. An extremely important synthetic route to ether preparation is the Williamson synthesis. It can be used in the laboratory to produce either symmetrical or unsymmetrical ethers. In general, an alkyl halide is combined with a sodium alkoxide to produce an ether. A sodium halide is the byproduct. The Williamson synthesis works best with methyl or primary alkyl halides. The alkoxide can be primary, secondary, or tertiary in nature. For example, sodium ethoxide reacts with iodoethane to form ethoxyethane or diethyl ether. If secondary and tertiary alkyl halides react with alkoxide, then the reaction proceeds via elimination. The tertiary alkyl halide reacts with alkoxide to form an alkene as the main product. The Williamson synthesis can also be used to convert phenols into ethers, as shown here, by means of phenoxide ions. Can you answer this question on your own? Draw the structures of the most appropriate reactants for the preparation of tertiary butyl ethyl ether 2-ethoxy 2-methyl propane by the Williamson synthesis. Give the overall equation. Look carefully at the ether we want to make. It contains a primary carbon on one side of the bridging oxygen and a tertiary carbon on the other. For the primary carbon, we need a primary alkyl halide with 2 carbons. Ethyl chloride would be a suitable choice. For the tertiary carbon, the suitable alkoxide is sodium tertiary butoxide, which consists of a tertiary alkyl group. Now, we can see the overall equation for the synthesis of tertiary butyl ethyl ether. Why didn't we use the alternative combination of reactants for the previous problem, that is, sodium ethoxide and tertiary butyl chloride? We had noted earlier that the Williamson synthesis is only suitable for primary alkyl halides. This is because when secondary and tertiary alkyl halides react with metal alkoxides, elimination reactions tend to occur and alkenes form. The reaction of sodium ethoxide and tertiary butyl chloride would form 2-methyl-prop-1-ene as the major product. Let's consider the physical properties of ethers. Ether molecules have a net dipole moment. The carbon-oxygen bonds are less polar and arranged in space such that the dipoles do not cancel. However, ethers cannot participate in intermolecular hydrogen bonding with other ether molecules. The boiling points of ethers are similar to the boiling points of alkanes with comparable molecular masses. For example, N-pentene and ethoxyethane have very similar boiling points. However, ethers have lower boiling points than alcohols. Butan-1-ol has a much higher boiling point than ethoxyethane. This is because alcohols can participate in intermolecular hydrogen bonds while ethers cannot. The miscibility of ethers in water is quite similar to the miscibility of alcohols with similar molecular masses. 7.5 grams of ethoxyethane can dissolve in 100 ml of water, just below the 9 grams of 1-butanol that can be dissolved at the same conditions. This is because ethers, like alcohols, can form hydrogen bonds with water. As a class of molecules, ethers are extremely flammable. They are volatile substances as well. Avoid this serious fire hazard. Never have open flames if ethers are being used in the lab. Generally, ethers have very low reactivity. They are among the least reactive of the functional groups that you will study. As the oxygen atom is attached to the 2 alkyl groups on either side of it, ethers are less reactive. Let us look at some important reactions of ethers. The ether linkage is quite stable towards oxidizing agents, reducing agents, and bases. The cleavage of the carbon-oxygen bond in ethers takes place only under vigorous conditions by acids. Hence, acid-catalyzed cleavage of ethers occurs only under drastic conditions. These reactions require an excess of hydrogen halides and heating. In the presence of hydrogen halides, an alkyl halide and an alcohol are produced. The alcohol formed under these conditions then reacts with another hydrogen halide molecule to form a second alkyl halide. Thus, when an ether is heated in the presence of excess hydrogen halide, two molecules of alkyl halide and a molecule of water are produced. For example, methoxyethane reacts with excess hydrogen iodide at high temperature to form a molecule each of iodoethane, iodomethane, and of water. Hydrogen iodide is the most reactive hydrogen halide in acid-catalyzed cleavage of ethers, followed by hydrogen bromide and then hydrogen chloride. Hydrogen fluoride is ineffective in these reactions. Let's look at the mechanism of this reaction in greater detail. In the first step, a proton is transferred from the hydrogen iodide to the ether to form an ethyl-methyl oxonium ion, which is a protonated ether. In the second step, which is the slow step of the reaction, the iodide ion, which is a good nucleophile, attacks the least substituted carbon of the dialkyl oxonium ion as shown. This produces ethyl alcohol and methyl iodide. Next, the alcohol that was just formed reacts with another molecule of hydrogen iodide and results in the formation of ethyl iodide and a water molecule. This happens via the formation of the intermediate oxonium ion as shown here. When tertiary alkyl groups are present in the ether, reactions with hydrogen halides will form a tertiary alkyl halide and an alcohol. This occurs because a different reaction mechanism is involved. It is an SN1 mechanism with a unimolecular slow step. Let's look at how the mechanism is altered when tertiary alkyl groups are present. In step 2, the dialkyl oxonium ion forms a carbocation as the less substituted alkyl group leaves. Notice that there is only one reactant in step 2, which is the slow step of the reaction. Then, in step 3, the carbocation attacks an iodide ion and results in the formation of an alkyl halide, which is the fast step of the reaction. Hence, the reaction is a unimolecular nucleophilic substitution reaction. Here is a problem for you to solve. Predict the products of this reaction. Notice that one of the alkyl groups contain a tertiary carbon. In the presence of hydrogen bromide, this group will form a tertiary alkyl bromide. The other alkyl group will form an alcohol. Alkyl aryl ethers also undergo acid-catalyzed cleavage. The cleavage occurs at the alkyl oxygen bond because the aryl oxygen bond is more stable due to its partial double bond character. When the alkyl oxygen bond breaks, phenol and an alkyl halide are produced. The phenol formed doesn't react further with another molecule of hydrogen halide to give an alkyl halide. Since the sp2 hybridized carbon of phenol cannot undergo a nucleophilic substitution reaction. Can you draw the structure of the major products that form when the molecule shown here reacts with hydrogen bromide? Since this is an alkyl aryl ether, ethyl phenyl ether, the alkyl oxygen bond will break. One product will be phenol. The other will be ethyl bromide. Ethers will undergo oxidation in air to form explosive peroxides. Compounds such as diethyl ether, hydroperoxide are unstable and shock sensitive. Hydroperoxides can form in just a few days if samples are exposed to air. Always follow lab safety rules. Never use old bottles of dialkyl ethers and dispose ether samples properly. Let us now look at electrophilic substitution reactions of anisole, which is an alkyl aryl ether. Anisole is the common name for methoxybenzene. The lone pair on the oxygen atom of the methoxy group activates the ring towards electrophilic substitution as shown in their resonance structures. Hence, it is ortho-para directing. The para isomer is the major product due to steric hindrance at the ortho position. The halogenation of phenyl alkyl ethers occurs at the para position by using bromine in ethanoic acid. No Lewis acid catalyst is required because of the presence of the ring-activating alkoxy group. Give the structure of the major organic product formed when this compound is reacted with bromine in ethanoic acid. The methoxy group is ortho-para directing. So, both the para as well as the ortho isomers will form. The para isomer is the major product. Hence, para-bromoanisole is the major product. Phenyl alkyl ethers will undergo Friedel-Crafts alkylation. Phenyl alkyl ethers reacts with an alkyl chloride in the presence of anhydrous aluminium chloride, a Lewis acid, and results in the formation of ortho and para isomeric products. The alkyl group of the alkyl halide will attach to the benzene ring at either the para or at the ortho position. For example, anisole reacts with methyl chloride in the presence of anhydrous aluminium chloride to form 4-methoxytoluene, which is the para isomer as the major product, and 2-methoxytoluene, which is the ortho isomer as the minor product. Friedel-Crafts acylation reactions are also possible. Phenyl alkyl ether reacts with an acyl chloride in the presence of anhydrous aluminium chloride as a catalyst. This introduces the acyl group at the para and ortho positions. Predict the products of the reaction when anisole reacts with ethanoyl chloride in the presence of anhydrous aluminium chloride. Under these conditions, Friedel-Crafts acylation will occur. The para isomer, that is 4-methoxyacetophenone, will be the major product. Phenyl alkyl ethers will undergo nitration reactions. For example, anisole reacts with a mixture of concentrated sulfuric acid and nitric acid to form nitroanisole. The nitro group is introduced at the ortho and para positions, and 4-nitroanisole is the major product.